Hello and welcome to another video. Today we have an MSI X470 Gaming Pro Carbon on our bench, and this board is supposed to have an USB overcurrent detection and is shutting down because of that. So it appears the board is working from what the owner said. It is booting up, but it shuts down because the USB is being overdrawn. This issue can have multiple reasons why it occurs. It can be a dead PCH, it can be a dead USB controller, it can be dead Zener diodes protection on the USB. There are diodes that get conductive as soon as there's 9 volts or 12 volts on a USB line that is supposed to be 5 volts, and then they are shorting to ground. They are protecting all of the rest of the circuitry and sacrificing themselves and leading the current and voltage to ground. So we will have to figure out what of that is the actual issue. It also could be the SIO that is partially faulty. So we will have to first go on with our usual checks of resistance. So let's take a ground connection and check our 24 pin. So checking 3.3 volts, has high resistance. Then we go into the 4th pin from the top, 5 VSB, high resistance. Then 12 volts, high resistance, and 5 volts, also high resistance. Let's check the CPU power, that has high resistance, and from 12 volts into the phase, also high resistance. That is good. Okay, so we have a problem with USB. And if we have a problem with USB, we might want to see for little regulators that are around the board, if any of those show low resistance, but there's basically only a single one that I was able to see. We will probably, I want to confirm the fault. So I want to see if we can power this board up actually and get it to the state where it shows us the USB over current. And if we get to there, we might actually be able to use a thermal camera in order to see if anything is heating up too much on this board. So let's then build the board up. I'm going to be using my 2200G to put it into here. We didn't do any visual inspection yet, which could be like a fault of the USB. Let's do that first. Let's see for some things. So let's see at the side here. We can see, oh, the board is really bent. Holy moly. You can see that it's bowed down inwards. Okay, that might be an issue. So the USB 3.0 right there has no bent pins. Then the SATA also looks fine, so no problems with that. Let's see, have a quick look. There's a really rusted screw at the back. There's multiple. Are those rusted? Looks weird. We will definitely have to have a look at the back area of this board. Man, this is so bent. Holy moly, this board. That it's even turning on. But nothing obvious at the back that is damaged. Let's have a look at the USB ports from the side. All of these pins look fine. We want to see for these golden contacts in there. All of them look fine. And the USB-C is hard to see, but I don't see any problems with that. So let's go over then to, if we have a look at the front, there are more SATA ports right here and USB 3.0 headers. But all of those also look fine. No bent pins, nothing like that. So that is not our issue for a quick physical inspection. Let's go over then to building this board up. 1 stick of RAM, the 2200G in here. We need a display capture because presumably this board is turning on because the previous owner said that it shuts down with USB over current. So let's get HDMI into here. Let's get a power button onto here. We need a cooler. Let's see, does this have a TPM header? It does. Let's see if we can connect our postcard onto there in order to see some postcodes. So let's see then for our passive power consumption, if this already, maybe even at the passive power consumption, we can already see that there's too much power drawn. And then we will shut it down and have a look with the thermal camera already. 120 milliamps, that looks very fine. Okay, let's hit the power button then. Okay, it does react to the power button. We do have a CPU LED. So if we are stuck at the CPU LED with 1.1 amps, and that might be due to the CPU not being supported. So let's go over to a 3100 then, because pretty sure that that is supposed to be supported in here. But with the 3100, we will also have to put a GPU actually into here. Yeah, now we get postcodes actually. As you can see at the bottom right there, we actually get postcodes running and we have way higher power consumption. Let's see now for a picture and see if this actually shuts down with USB overcurrent protection. So there's the picture. And let's see now what it says. Because the power consumption doesn't look abnormal. The power consumption looks like something I would expect from this board. And the board restarted on its own. That's probably just normal with the new processor and RAM. And there it is. Overcurrent have been detection on your USB device. System will shut down after 50 seconds to protect your mainboard. Okay. Well then. That's the actual issue that we have. Everything that the previous owner said seems to be correct. So we will then... So let's take all of the heat sinks off of here. And get everything detached from this board for now. In order to then check with the thermal camera if we can find an actual hotspot. So let me strip this down quickly. So let's get the post screen out of the way. And the board is fully stripped down. And we have today the opportunity to use this P3 thermal camera from Thermal Master. This is an always focusing Thermal Master. And it claims it can see up to 0.25mm resistors, from 8mm to 80 meters adjustable focal length, and up to 600 degrees Celsius range. 8mm macro lens. And it has a resolution of 512 times 384 Super IR resolution. And this is very, very good. Like, I haven't opened this thing yet. I have opened it up, but I haven't used it yet. And you know, I've been using the P2, the previous one, to this. And I love the P2. The P2 is great. And I'm really interested in how great the P3 will work. So we have some instructions, a quick start guide, and probably, oh yeah, the extended warranty. Let's put that to the side. Then, let's see, this is probably cables that we have here. Yes, this is a USB extension cable. Very nice. Then we have a carrying case. And in the carrying case, we actually have the P3 unit itself. This one is bigger than the P2, probably because of the focus. And we do get an adapter for, what is this, iOS? Yeah, the lightning adapter. Okay, we don't need that. So, thermal camera looks good. Let's get that hooked up to my phone. So, I got the actual thermal camera now attached to my phone. And now I will have to do some figuring out about this, how to adjust it properly. So, let me do that quickly, some adjustments, and then we can actually have a look around the board. We actually got it now working. And I got to be honest, I'm really impressed with the focusing of this. Like, this can definitely go into an interesting or a really good range of focus. Like, I'm very far away from the board. And you can definitely focus well onto this. Like, the adjustment on the lens is way bigger than I thought. That you can actually see it from above as well. You can see in my face cam, you can actually see how far I'm actually from the board. This is quite some distance to my workbench. This is cool. So I don't have the best setup to capture this because of my phone and everything, but let's get power into the board and actually see if we can see things heating up and how well we are able to focus onto them. So let's get passive power consumption in here. So 83 milliamps. Let's now have a good look at what we can see that heats up. So we can see something heating up here. Let's go close to it because I want to see how well we can focus onto that. Oh yeah. Oh yeah, that is insane. That is so good. Like, I'm so close with the thermal camera now. Adjusting the focus onto it. And you can definitely see O4, O2 components on this. Like, I'm capturing through camera onto my phone, which loses some quality, obviously, but this is so good. Like, this is just normal heat up, 33 degrees on a chip that provides VPP. That is nothing special. So let's go to an overview again. Adjust the focus like that. And now have a look where we can also see heat up. So this is 3 VSB that is heating up there. This is just the controller that is heating up here a little bit. Nothing special. So let's go out again. I'm really impressed with this. There's more heating up right here. This is a USB controller actually that is heating up a little bit. But not abnormal heat, just a little bit of heat up. Let's go back out again. Probably wrong direction. Yep, you're wrong direction. Let's see, what else does heat up? Nothing really heating up anymore, but we are also in passive state. So yeah, just some reflections. Really cool so far. Okay, then so in passive mode, there's nothing heating up too much. So we want to see when this board actually tries to boot up, what will go into the thermal, into the USB overcurrent. So we will have to press the power button, then have a good look around the board. Let me connect my power button back onto here. So it is important you won't be able to see the board, but you will be able to see the power consumption right there. So have a good look at the power consumption when we try to boot this up. So hitting the power button, and let's see if we can see any abnormal heat. Something heating up there. Something, okay, this is just the power for the PCH. A little bit of heat up down there. Some heat up of the drivers that are normally cooled. Definitely some heat up under the USB audio. Some more heat up around the SIO. Definitely heat up around the PCH. So let's get a little bit closer to the PCH. The PCH is actually getting quite hot. But I don't see like a hot spot or anything. I will probably have to clean this off a little bit better. But there's not like a single component except that. That will be interesting. That's just a resistor at 35 degrees. I don't think that has anything to do with it. Okay, let's have a further look if we can getting zoomed down on some of these, like this controller, but also there's nothing too much heating up here. This is the SIO now, and the bottom left, probably an audio chip or something like that. Just little bits of heat up. USB controller that has heat in the middle of it. And yeah, nothing more really to see here. Man, I'm so impressed with this camera. I love the quick adjustment of this to go from like far away to getting really close. But yeah, nothing really heating up too much here. Okay, so it is stuck on a VGA LED because I don't have a GPU in here. So let's get the actual post screen. Let me see an actual post screen and get this built up more, because maybe then the USB will be more apparent. So now this board should be booting up with actually getting into a post screen and showing the message then. And I want to have a good look around the board now. So the board did boot and it shut down. Okay. So the shutting down definitely works fine on this board. So there's no actual heat up of anything like that is obvious. There's a good amount of heat around the PCH, but that is expected. What is really weird is that there's no LEDs running on this board. And that leads me to the belief that it might be the LED controller that is shorting the USB also. And the controller in question is, I think, this one right here. That, which is here. This controller, as far as I know, is responsible for the LEDs. And this not running and the USB being a problem might have a correlation. But yeah, we will have to go into a board view because the thermal camera is doing a great job of showing that nothing is actually heating up too much. So let's find a board view for this board. Let's get the passive power consumption out of here. So we are now in our board view. And there's actually a lot of things that we can check now. One of the most obvious things is USB, is the actual USB headers that we have. And they all being fed by something that is 5V RU USB. And this is being created by these MOSFETs right here. And by these regulators. And this switches between 5V VSB being the supply and actually 5V dual, I think, being the supply for this. Not 5V dual, the actual 5V you can see. VCC5, that is the actual 5V coming from your power supply that is then being put into the USB. We will have to check the resistance of this and if 5V actually is there or not. Because this then goes to a lot of places. These are capacitors, a fuse right here that goes into the PS2. Then another fuse going into the normal USB headers. Then next two fuses here. One going to the regular USB and one probably to the USB-C right here. Then another fuse to just 2.0 headers again. Then this is where it actually comes from this P-channel and N-channel MOSFET. That is not fitted. 40k ohm resistor, 200k ohm resistor, 500 ohm, 10k, 10k. And there's an actual chip that takes this. No idea too much what this is. And then there's another linear regulator probably for enabling that. So let's see, what is this chip? This chip. Oh, this is for the USB-C. Yeah, okay. Pretty sure. Because this carries PCIe, something similar to PCIe, and then goes to the USB-C right here. So this controller will also be interesting for us. So this is one of the big USB lines that we will have to check. if that 5 volts is correct or not. Then another thing that we can check, on each of these pin headers, there's a USB VCC also going to fuse again. And we can check that by USB 30 VCC1. This goes to capacitors, a fuse, and to this one. And let's see the other side of the fuse. 5 volt F USB, front USB. This is another 5 volts that we can check, again with the same topology, P-channel MOSFET and an N-channel MOSFET, in order to switch from 5 VSB and the actual 5 volts, and a few fuses where these connect. So there's one fuse for the header right here on the side of the board. Then we have another fuse going down to this USB header right there. Then a next fuse again to USB 2 header. And another fuse here going to USB 3 header. So this is more of USB connection. Then let's see if this LED driver takes a USB VCC somewhere. It takes LED VCC. Okay, this seems to have a different kind of VCC. So big question is, will this be connected somewhere to like... No, this is all just connected. These all are connected to LEDs, so you can individually see. It seems you can. Oh no, they all turn on and off together probably. Okay, because they're on the same line. And then there's some headers and some capacitors. Okay, so I do not know if this LED VCC also is the USB overcurrent or not. If that can actually be the case, because the weird thing is that none of the lights are on, but that also could be an issue because of it being disabled in the BIOS. That could also be the case. Let's also see, let's go from the VCC5 and see where that all goes in order to check where all we can also go. Is this a copper connection to DDR control? Okay, yeah. I'm searching for places where this, for example, this goes into another fuse for a for an LED connector, but okay, that probably won't be an issue. There's another header, there's another MOSFET, but this is for the DDR. Okay, let's see, there's another MOSFET here close to the USB. More MOSFETs. This is the MOSFETs for the USB that we've seen before. And this is for 5 volt dual. This is actually also something I want to have a look at. But if 5 volt dual was shorted or had low resistance, I would expect the board not to turn on at all. So I don't think that will be a problem. And this is the other USB that we've seen that has a problem. Then these are just high value ohm resistors. There cannot be basically anything shorted through that. Another NCT chip, but this is for vCore, I think, so this must be working. Another RT, something for the LEDs, okay. Some more LED control, and this is a doubler or a MOSFET driver. But this also probably won't be the problem because the vCore is working. So let's then first have a look for this 5 volts at the bottom there and the 5 volts coming out of this one and see if any of those look weird or have weird readings. So let's go under the microscope for that. So this is the USB at the top left. Let's have a good look around here if there's anything damaged. Oh, that is that a soldered fuse? That fuse looks like someone had replaced that. Because this is how they usually look. And this is how this one looks. That looks like someone had been here before and has tried something here. Interesting. But I cannot see any other work or anything being damaged here. Just that fuse looking very weird. Let's have a continuous look around this USB. Okay, I don't know if this is soldering or if this. Yeah, okay. These fuses seem also to have been soldered too, and there's a blob of solder right there. So this had previous work done to it in this area, which is very weird. Very weird. Because you can see also corrosion right there on that top capacitor right there. Interesting. Is this button working? Yeah, the button is able to be clicked. Okay. Yeah, and this fuse is also soldered too. Interesting, interesting. So I think the problem will probably be somewhere in this area, not the bottom right area. But let's also have a look around there for the front USB, if we can see anything damaged here. So we have the same topology right here with this P-channel MOSFET and this N-channel MOSFET. And let's have a look now at the fuses that are also here. We have fuses at these front panel headers, and these look fine. Like, these fuses have not been soldered to. Yep. So interesting. The plot thickens. There has actually been work being tried to do here. Let's see if we can get further than the previous technician that has tried to do something here. So let's have a look here. So we need resistance readings. So let's get a good ground and let's see. This is, I think, the 5 volts. This has high resistance. The gate driver has high resistance, and the actual output of this has also high resistance, doesn't it? Let's see, can I get onto you from here or like from there? Yeah, high resistance. No problems here. Okay, that doesn't mean that this area is good, because that could still mean that the power isn't passing like it should. I want to check some of these fuses, if these fuses are still intact. So let's see, where are we? Right there. Yep, this fuse is fine. And I think these are poly fuses. Not sure if these are resettable or if these just blow once. So this is also fine. Also a soldered one. This one doesn't look like it had been replaced or anything. Let's check here. Also low resistance. Okay. So all of these fuses seem to be fine so far. Let's check for these two that have been soldered here. This fuse is also fine. Next fuse. Also fine. Big question is, were these fuses fine before, or were they only fine after they had been soldered to? Also fine. Let's see, is there any more? Or was that the last of them? Yes, I think that was the last of the fuses. So yeah, no actual shorts so far. The big question now will be if the 5 volts is actually being passed down here properly. Like, if the topology with the P-channel MOSFET still works properly in the N-channel MOSFET. Okay, let's then put power to this and check for values. So let's see right here. This should be 5 volts. 0.5 volts. Really? 0.6 volts. Is maybe the USB is not enabled in passive mode, because that has 5 volts. That has 0.7. And that has 5 volts. Okay, but no 5 volts there. Let's check a fuse somewhere, like these ones, if we have 5 volts on them, because it seems like we do not. 0.8 volts. Okay, that already seems weird, that we have 0.8 volts here. Let's check how it behaves when we try to turn this on. So, and now, what kind of voltage do we see here? 5 volts, actually. Okay. So we actually have 5 volts here. So the voltage that should be here is there. Yup. And none of these heat up. Interesting. So what is interesting is that we have 0.7 or 0.8 volts in standby mode, but we have normal 5 volts here while it is in powered mode. Okay, let's then check the bottom right for USB, how this behaves with standby and not standby. So currently we are in standby mode again. As you can see, we have 80 milliamps of power consumption. Let's have a look. This should be probably 0, yes. And the output, the other one had 0.7. And this still has 5 volts or like 4.8 volts on here in standby mode. Interesting. While the other one did not have that. But the question is it just draining? Then let's turn this board on and see what voltage we have here when it's turned on. When it's turned on, we actually have 5 volts on here. And none of these heat up. Okay. Interesting. Let's turn this off. Let's drain this a little bit. And I want to see if this topology right here also has 5 volts in standby mode or not, if this is all drained. So currently it is drained, 0.4 volts. So let's get passive power consumption into here. And let's see if this is now 5 volts or not. No, this has 0.4. Okay, so they are similar to each other. Both of them show the same reading in passive mode. And when you actually turn this on, we have power consumption now. As you can see, we now have 5 volts there. And we do have 5 volts at the other one. Yeah, both have 5 volts. Interesting. So that does not seem to be the issue here. But it's weird that both of the like a lot of the fuses have been soldered to at that point. What I want to see, because these are polyfuses that can be reset, I think. These could show low resistance while it's off, but actually could not let voltage through when it is actually being on. So what I want to do here is I want to power this up and then check both sides of the fuses for what kind of voltage they have on them. So let's check. We are going to turn this board on and let's check for both sides of these fuses. So this side has 5 volts. This side has 5 volts. Okay. So this one doesn't seem to have an issue. Then let's check the next two. Let's check these two. This one 5 volts. This one 5 volts. That 5 volts. And that has 5 volts. Okay. So no voltage drop anywhere here. Let's check on this fuse right here. 5 volts on this side. 5 volts on that side. Let's check here. 5 volts on this side. Okay, what is happening on this one? No, also 5 volts. Okay. And then one more right here. 5 volts here. 5 volts there. Okay. All of these voltages seem to be fine. Let me check a few around the front panel headers. If they go down anywhere. So I'm in the schematic because I cannot go any further currently with the board. I want to show you what is in the schematic. So we have a chip, U60 right here, UP7501. This has two 5VSBs that goes as derivatives that are enabled through S3 and S5. These later feed our USB lines, and we've seen that these USB lines are all 5 volts. There doesn't seem to be any problem with that. This is like the main starting controller. And then these signals go further into these here. This is what we seen, what feeds the USB. You can see all of the USB headers right here, and the PS2 port. How much amps they are valued. All the fuses you can see, and then you can see the topology with the P-channel MOSFET and the N-channel MOSFET. So that there is 5 volts, and all of these 5 volts after the fuses and before the fuses seem all to be fine. So I wasn't able to find any of these that they are shorted or have low resistance or anything like that, or have a low value of the USB itself. Then there's more here. This is for the rear. This is at the top left that we've seen, and this is the front. This is at the bottom right of the board. You can see same topology, and this also seems to be fine. Then the front USB. All of these have protection. Like you can see, ESD ones. All of these have ESD protection. This is the header itself, and there are overcurrent signals that are going out of these from N-channel MOSFETs. And we want to see where these overcurrent ones go, because these go to the PM, which is promontory, I think it is called, and this is probably then the PCH. Let's see for that. Yeah, as you can see right here, promontory. This is the PCH where this goes into. So you can see right here that 3 VSB goes into each of these overcurrent lines here. PM0, PM OC0, PM OC1 to up to 7. And all of these connect into the PCH then. And they are even labeled, as you can see. The rear USB, rear type A, this is probably the front USB. Yeah. And we will have to see if all of these have the same voltage or not. Like, I don't know, because they are pulled up to 3.3 volts, it probably expects each of these signals to be 3.3 volts. And they probably are able to be drawn low to ground if they have a fault condition. Like you can see here. Yes, you need this USB VCC to enable this gate right here. Let's zoom down a little bit. So we want this to be high probably, that this is 3.3 volts. This can be drawn low to S2. This is drain source. This is just the N-channel MOSFET that gets enabled. And that can be connected to ground if G2 has voltage. When does G2 have voltage? G2 is being fed through a pull-up resistor right here to VCC5. So 5 volts comes in. 5 volts is always present. This is from the 24-pin connector. 5 volts goes into this line, enables G2, which connects D2 to S2. And it also is from D1, so drain 1. It can be connected to source 1 if G1 is enabled. So we need G1, which is USB 2.0 VCC1, to be enabled on this gate in order to draw D1 to S1. So this line then goes low through this resistor, and this MOSFET goes low to ground, which means G2 gets disabled, which means D2 is not connected to S2 anymore. So D2 is just being drawn up by the 3 VSB. And that's what we want to find out, if all of these signals are high or not. Because all where they go, they can be drawn down to ground. And we need to find out if this signal is high or not. So let's find these resistors right here, because on these resistors we will easily be able to check that. Let's find these on the board view. So on the board view we can see 2 of these resistors. They take PMOC1 and PMOC0, and we want to see if these have 3.3 volts on them on both sides. And then we will also have to check the rest of these resistors, like R557, where this one is. There's another one here, for example, and we will have to go through each of these resistors here. So let's check these resistors one by one if they have voltage on the other side, and if they trigger the overvoltage protection, the overcurrent protection. So we see right here we have 3 volts on this side, And we have 3 volts on this side. Let's turn this on. The board is now turned on, and we still have voltage on both sides on both of the resistors, right? Yes. We have voltage there. We have voltage there. Okay. So let's move on to the next ones. So the next one is that one that we can see right here. And it has voltage on this side. And it has voltage on this side. I think this will be the next one. Has voltage here. And has voltage here. So these two are also fine. Let's move over. It might be these two next then. Let's see. Do these have 3.3 volts on them? Yeah, 3.3 volts there. And 3.3 volts here. Let's turn this board on again. 3.3 volts there. And 3.3 volts there. Okay. So all of these are fine. So, and the next ones that we need are these two right here. So let's see. They have 3.3 volts there both. And let's see on the other side. 3.2 volts here. And 3.2 volts here. So none of these seem to be our issue here. So the overcurrent protection isn't being triggered by this. So let's go back to the board view. So we were able to see that all of these resistors carry the voltage on its other side as well. So, big question, what else could there be shorted? Let me scroll a little bit through this. So I'm currently really stumped on this one. I went ahead and checked all of these. So all of these protection diodes, I've went into the board view, tapped them in, looked at them, and then checked all of the contacts, whether they have shorts or not, and the corresponding resistors, capacitors where they connect to as well, in order to check out if any of those were shorted. But I couldn't find any shorts on any of them. I checked all of these. I went ahead and took all of them, like this one also, put them in, looked at them, and then looked for their resistances, and I wasn't able to find anything shorted. The next step of operation currently that I'm thinking of doing now is I want to take out whatever could be at the heart of putting out the power fault signal. Like, for example, I think there's like 2 things that can put a overcurrent out. Like you can see, this controller UT1 can put out a type C overcurrent, and I want this to be gone. Like, I want to desolder this probably in order to see if this puts a fault out somewhere. There's also this fault right here that comes from this controller U26. Let's see what that is. That is this controller right here, U26. That could also be putting out a fault condition. Let's see what else of fault conditions can there be here. There could also be this controller theoretically putting a fault onto one of the USB lines. So we could also take this off. This is U34. So these are these 2 chips then. And then there's theoretically this chip right here. The U60. Where is this one? This one right here. I think I will start taking off this chip first. I will take that UP controller off, and then I want to see how the behavior of the board changes. If that does not change anything, I will go ahead and I will be desoldering this one probably, U26, which is that one. And if that doesn't work, I will go ahead and desolder U34, which is that one. But that one, I don't think, this is a PCIe switch. I don't think, it can put a problem on there, but it's unlikely. Yep, and I will just have to go and figure stuff out here. Like, I haven't had one that was this resilient to find out what the actual problem is on the USB lines. So yeah. So guys, I want to show you something. I've been on this for about 5 more hours. I've really gone crazy about this. I've desoldered and resoldered so many things. And at one point, I started to take another mainboard out of my stash that I luckily have. I have another X470 board, an MS7B79. This is in Gaming Plus Max that is known good and working. And I've been comparing it to my board, which is the 7B78. And I've been searching high and low for different signals that indicate overcurrent. And I have found something. There's a signal called APU USB overcurrent. That is, I think, from an AND gate. This is a dual AND gate that takes USB XOR 0 and core type 1. Has 3 VSBs, VCC and a ground. And I want to show you the readings of the board. So let's go over to the faulty board that we've been working on. And let's see for the readings. The faulty board is actually this one, which basically looks the same way, is the same component that also takes USB XOR 0 and CPU 1 type select 3 VSB and gives out APU overcurrent 0. So let's check the values that we have on our board here. So, and this is the board now. Let's see. We're going to turn it on. You're not going to see the power consumption because I'm using a standard power supply. So, this is our component. And let's have a look. Right pin has 0 volts. This is ground as far as I know. Middle pin, 3.3 volts. First pin has 0.7 volts. Fifth pin output has 3.3 volts. You could see the post screen in the top right, which says overcurrent. And 3.3 volts. So 1.2 volts, 3.3 volts, 0, 3.3 volts, 3.3 volts. Let me now get the other board, the other X570 board, and build that up, and we're going to compare. So right here, we have the other board that will now be posting. We will be able to see that it is booting up. And let's see that same component. So on this output, we have 0, where we had 3.3 on the other one. This one has 3.3 volts, just like the other has 3.3 volts on that pin. Let's now check the inputs. This is ground, I think. Yes. Then the middle pin has 3.3 volts, which the other one had as well. And that left pin has also 3.3 volts. Where on the other board, we saw, what was it, 0.7 volts or something like that. And the board should be posting. It isn't posted yet. Let me take a different PCIe slot. That is probably the issue here. So that we can see an actual post screen that this board is actually working fine. So keep in mind those values that we have measured there. There we are. There's the post screen coming. It just now rebooted. There it is. And this is the working X470 that I've been taking as reference. So let's now build everything back to the non-working board that we have been working on. So now we are back at our non-working board. And what we will do now is, the big difference was the bottom left pin that had 0.7 volts instead of 3.3 volts that the other one had. The marking on the component is slightly different, but it does do the same thing. So if we now do the following, we connect up 3.3 volts to that pin right there, to that input, and now we are going to turn the board on. And there the board turns on and it posts. No more message about overcurrent. There's a BIOS screen. I cannot believe it. So for whatever reason, the first input in the bottom left is wrong, which is why our APU OC has a fault. So we get an overcurrent protection via that line. It has nothing to do with any USB device. It is actually something that is connected to the CPU, a CPU signal. So there is the middle pin of this thing is actually connected to USB, the USB delivery. But the important thing is the left pin. So let's have a look where that pin comes from. So the signal is the type 1 CPU select that is incoming. The important thing is this has a pull-up resistor. This has a 47K pull-up resistor. 5 VS to 5 VSB. So this line could be anywhere from 0 to 5 VSB. And then there's a lot of N-channel MOSFETs connected to here. This is the actual component that we've seen. And then there's a lot of N-channel MOSFETs connected to here. Some dual, some single. And it always goes to gates except a single time. So only from this transistor here, this can change the value of it. Because for the others, if the others are not shorted, these only go to gates, which means the gates are like a dead end. They never lead it into anything. So none of these can drag them down except this one, because this one is connected to the drain. Let's see VQ4 what that is for in the board view. So what we can see, this is the aim4 CPU type circuit. This is just transistor right here where D is our type 1 select, and this should be 5 VSB except if it gets taken down to ground right here to type select and to core type through core type right here. And now the big question is, what voltage do we have on this transistor for its gate? So I would expect that there's some voltage on this gate right here in order to that pulls this one down a little bit. So let's check VQ4. So now under the microscope, let's turn this board on once more and let's see what do we have on this here. This is its gate. The gate has no power. This has nothing. And this one probably then has 0.7. Okay. So it's this one is actually not enabled. So this doesn't pull it down. Because you can see this gate is 0. So these shouldn't be connected. So then the question is our 40K ohm resistor damage that is pulling it up to 5 volts. So let me search where that is. So this right here should be 5 VSB, which it is, and that then is the output for the type select, and it has 0.7. So the question is, why is that? Do we get low resistance there? I want to see that while it's on. No, we don't have low resistance on that. So the question is that resistor faulty or not? Let me get the power disconnected. Let's see for the resistance. It should be 4.7 or 47K. And it is 47K. Interesting. So what is dragging the signal down? I cannot tell you. Because this one isn't faulty, right? Yeah, we have high resistance here. So this isn't faulty. Okay, let's try it again to turn it on then and see for the resistance once more. Because the question is, why does the 5 volt not connect to there? Because we do have 5 volts here. So why isn't it 5 volts there? It's 1.7 here, interesting, through a 47K ohm resistor. And this doesn't have voltage on it. And let's see it to ground. No, it has high resistance. I'm in my 20 kilo ohm range, and it has high resistance. And if we turn the board on now, this resistance isn't changing. Yeah, the resistance is still high. I'm not getting a reading on it. But why, I cannot tell you why it is that we don't have voltage then there. Like, where is it going? We have 5 volts there. How is it that there is nothing here? Where is it going? Because there's no low resistance on here. This one is not enabled, and the others are just um going to gates and nothing else. I want to see something. I want to change out that resistor for something lower value. So maybe like half of it, because the thing is that this is just basic ohm laws. If you have 5 volts through a resistor and there's no load on it because the other side isn't shorted, there should be those 5 volts at the other side of the resistor. But obviously there has to be some kind of load. So that means there needs to be amps that is being drawn into that line. I cannot see those amps that are being drawn. But those amps are so high that the voltage is breaking down because the resistance is high. So we want to lower the resistance for more current to pass and the voltage not to drop down. So we are going from this 47k ohm, I'm probably going to put like a 22k ohm resistor into there in order to find out if that will relieve this situation and make it that we actually have voltage on the other side of that resistor. So let's take the soldering iron and remove this here. There's the resistor off. Let's now get a different lower value resistor. And here we are putting a 22k ohm resistor in. So we go a little bit lower than half of what was there before. So let's hot air it quickly in place, that it will sit properly. There it is, in its place. Let's now clean this off. I don't know if this will already work or if we have to go lower than that. So area is clean. Let's now see how this board behaves for the voltages on here as soon as we now try to power this up. So we have it connected. Let's now see. So right there, we now have 1.8 volts. It definitely has gone up a little bit. Now the big question is, what will happen if we now try to turn on the board, and to what value that will go now. So now we have 1.9 volts here, where we had 0.7 before. Let's see if that is enough for the board to not power fault anymore. Okay, the board is stuck at a CPU LED. Interesting. Let's turn this off and try this again. Interesting. This led it to have a stuck CPU LED currently. Interesting. I will have to think about this and try a little bit out. So, we have a single 2-input exclusive OR gate. This is not quite the same like I thought, but if we read here, if the input is low, the other input is reproduced in true form at the output. If the input is high, the signal on the other input is reproduced inverted at the output. So we had the case that the input was low. We had one input that was 0.7, 1.2 volts, something like that. And the other input was 3.3 volts, which got reproduced at the output then. This is why we had 3.3 volt at the output. The other case is, if the input is high, which we now have because we saw that a lower value resistor in there, the signal on the output is reproduced inverted at the output. And inverting 3.3 volts, this will go to 0 volts because it cannot do minus 3.3 volts, but it goes to 0. And this is what was missing on our board. The big question is why? Because the resistor has the exact value that it is supposed to have. It has 47, it had 47 kilo ohms. And now putting a lower ohm resistor now did that. The only thing is that some of the MOSFETs that is on here, anything you can see in yellow here, something here got leaky. Or it's even this component that is dragging it down to ground. Who knows? Because all of these N-channel MOSFETs here, no matter if it's a dual one or a single one like these ones, they only have connection to the gate. And the gate is isolated from source and drain. There's a capacitor basically between them. They are not directly connected. There should be no current anywhere being gone from these gates. None of these should be able to lead any current down to ground. And this one is not enabled. We've checked this one, where this could be connected to ground if we have a voltage here, but I didn't see any voltage here. I checked this one. There's no voltage here, and I've checked to this connection to ground. There's also no connection to ground. There's high resistance to ground. Like, I do not know what the true fault is here, but we found a way to fix it. And I will be now updating the BIOS, trying out different processors in there. And yeah. And here we are. The board is working. The board is now in Windows. I need to be testing all of the functionalities, all of the USB I want to test now, just to be sure that they are working. The Ethernet is working and audio is working, which is a great sign already. M.2 is working, PCIe seems to work. The LEDs, I will have to see in the BIOS why the LEDs aren't working. I will flash the BIOS also on here. And I still need to put back the USB-C controller of this board. I've taken that off because of seeing if that is putting a fault onto here. But yeah, I do not know what to tell you on this board. I could only tell you the symptoms of it and a workaround. I cannot tell you what the actual fault of this was. But I still really enjoyed this video. Like, this was really interesting. I learned so much about the overvoltage condition of a board. Like, and without the other X470 board, I wouldn't have been able to fix this. Let me show you. This is the other board that I've been taking for reference, and this is also an X470 MSI board. And only with that, I was able to fix this one with going to cross-referencing different USB lines and seeing for what voltages should be there. I want to continue this video just a little bit longer, even though it's very long already. I want to test the thermal master camera in the case of what we've done with the top-down camera, where I have one board where I want to quickly get some results in how it looks like if we have a shorted VRM and a short on the board. So this board is done. I will now only continue with seeing for the thermal camera. That has helped us greatly at the beginning of this, like showing that there was no actual USB device shorted in here, but actually just a resistor or a weirdly power line that is being drawn to ground somewhere. So let's switch over to the other board. So we have a board that has a shorted V-core, shorted 12 volts, and we now want to inject voltage into here in order to find out how well the thermal camera can pick that up. So now we have a VRM short. You can see it with 1 amp at 170 millivolts, which is basically nothing. And we can see also nothing here, just some reflections. So let's higher the current here. So we're now at 3 amps, and we can already see which MOSFET is getting hot. That is pretty insane, because this is very low power, and we can already see we have one heat spot. And if we now go close to that heat spot, and if we then zoom down, we can see this so fast that this MOSFET is heating up. And if we just give it more current, it only becomes more apparent. But it was already apparent at like 3 volts. And if you go then up with the current as well, like this then easily becomes apparent. I'm really impressed. There's one more test I want to do with this, where I have another short circuit prepared for this. So there's another short circuit now on this board. Let's now zoom out again and see if we can find anything here. And we see some heat where the wire is soldered to, but it isn't yet obvious. Let's raise the current. We can see more heat there, but it isn't. It does get more apparent, but it isn't as much as I would want it to be. So we're now at 8 amps, and now, yeah. So this torture test is also too much for this. It does see that there's more heat, but it's basically, this is a 0 ohm short that I've made with the wire right here. But yeah, you cannot see that properly because that short is just too much. None of the cameras that I've tried so far have been able to spot this. This is 10 amps now, and the wire is heating up way more than anything else can heat up here, like the actual short. So yeah. Okay, but let's go down from those 10 amps that we've been drawing. But for the VRM shot with a V-Core, that was pretty good. Like, that was a realistic use case, and I got to say, I'm so impressed with this camera. This little thing is just awesome. Like, it is really, really good. If you're still looking out for a thermal camera, I can recommend this thing. Like, this is insane. This is about 300 euros, I think. Somewhere in that neighborhood. And definitely worth the money. You get this, you will probably never need another thermal camera for electronic repair. I'm properly impressed with them. So thank you very much, Thermal Master, for sending out this P3 thermal camera. It is a great one. I have had great pleasure to use this. It helped me definitely on the X470 because I was able to surely see that there was no short circuit on that whatsoever. And yeah, and then confirm the other fault later. And thank you very much for them. Thank you for your patience if you got through all of this video, which is probably 1.5 hours long or something like that. Thank you so much. If you want to get one of these current meter devices, email me. They're linked in the video description, just like all of my tools. Thank you so much from the bottom of my heart for sticking with me on this very hard repair. And I hope you learned something and it was interesting. Thank you very much, and goodbye.